Grounding Concepts and Applications by Vijay M. Soares, published in 2005, is a highly respected text on grounding. It is widely used as a reference in the field due to its comprehensive coverage and depth of technical information. Let's explore some of the book's strengths. Firstly, the book provides a thorough understanding of grounding concepts. It delves into grounding theory, measurement techniques, design principles, and safety aspects. Secondly, Soares emphasizes the real-world implications of grounding. It discusses various applications in industries such as electrical power systems, telecommunications, and lightning protection. Thirdly, the book includes numerous empirical data, field measurements, and case studies to support the concepts and recommendations presented. And fourthly, Grounding Concepts and Applications is recognized as a standard reference in the grounding community. It is frequently cited by engineers and researchers in the field. Now let's look at some considerations. The book is highly technical and requires a solid foundation in electrical engineering to fully grasp its content. The book can be expensive, especially for students or individuals on a budget. The field of grounding has seen some advancements since the book's publication in 2005. While the general principles remain the same, there may be some minor updates or developments that are not covered in the book. While Grounding Concepts and Applications is a solid choice, other texts may be more suitable depending on your specific needs and preferences. Grounding and Bonding Handbook for Buildings by Douglas J. Smith, published in 2014, focuses on grounding and bonding in buildings. It provides practical guidance for electricians and designers. Grounding and Shielding Techniques in Electronics by Christopher Marsh and Roger Green, published in 2000, emphasizes grounding and shielding in electronic systems. It covers topics such as electromagnetic interference (EMI) and electrostatic discharge (ESD). The IEEE standard for grounding and bonding of electrical equipment, IEEE Standard 80.2018, is the official IEEE standard for grounding and bonding. It provides comprehensive requirements and guidelines. Grounding Concepts and Applications remains a valuable and comprehensive text for grounding professionals. Its in-depth coverage and practical applications make it a highly recommended resource for those seeking a thorough understanding of the field. However, for those seeking a more practical or specialized text, other options may be more suitable. Grounding is a critical aspect of electrical safety. A properly designed and installed grounding system protects people and equipment from electrical shock and damage. It also helps to ensure the reliable operation of electrical systems. Grounding systems work by providing a low impedance path for fault current to flow back to the source. This allows the overcurrent protection devices, such as circuit breakers and fuses, to quickly clear the fault and prevent further damage. There are several different types of grounding systems, each with its own advantages and disadvantages. The most common types of grounding systems include the solidly grounded system, the impedance grounded system, and the ungrounded system. In a solidly grounded system, the neutral point of the electrical system is directly connected to ground. This provides a very low impedance path for fault current to flow, which allows the overcurrent protection devices to quickly clear the fault. Solidly grounded systems are commonly used in residential and commercial buildings. In an impedance grounded system, a resistor or reactor is inserted between the neutral point of the electrical system and ground. This limits the amount of fault current that can flow, which can help to reduce the severity of ground faults. Impedance grounded systems are commonly used in industrial facilities. In an ungrounded system, the neutral point of the electrical system is not connected to ground. This means that there is no path for fault current to flow, which can make it difficult to detect ground faults. Ungrounded systems are sometimes used in applications where it is important to maintain continuous operation, even in the event of a ground fault. Grounding conductors are used to connect the non-current carrying metal parts of electrical equipment to the grounding system. This helps to ensure that these parts are at the same potential as ground, which reduces the risk of electric shock. Grounding electrodes are used to connect the grounding system to the earth. This helps to dissipate fault current into the earth, which further reduces the risk of electric shock. The size of the grounding conductors and electrodes must be sufficient to carry the maximum fault current that could flow in the system. The National Electrical Code (NEC) provides detailed requirements for grounding systems. These requirements are designed to ensure that grounding systems are installed and maintained in a safe and effective manner. Grounding and bonding are closely related concepts. Bonding refers to the practice of connecting together all of the non-current carrying metal parts of electrical equipment. This helps to create a low impedance path for fault current to flow, which reduces the risk of electric shock. The NEC requires that all electrical equipment be properly grounded and bonded. Ground testing is an important part of maintaining a safe and effective grounding system. Ground testing involves measuring the resistance of the grounding system to ensure that it is within acceptable limits. Ground testing should be performed on a regular basis, especially in areas where there is a high risk of ground faults. Lightning protection is another important aspect of grounding. Lightning can cause significant damage to electrical equipment and can also pose a serious risk of electric shock. Lightning protection systems are designed to protect buildings and equipment from lightning strikes. These systems typically include lightning rods, grounding conductors, and surge protection devices. Surge protection devices, SPDs, are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, switching operations, and other events. SPD work by diverting the surge current away from the protected equipment. Grounding and shielding are important techniques for reducing electromagnetic interference, EMI. EMI can cause problems with electronic equipment such as computers and communication systems. Grounding and shielding work by preventing EMI from entering the equipment. Static electricity can also be a problem in some environments. Static electricity can damage electronic equipment and can also cause fires and explosions. Grounding and bonding can help to reduce the risk of static electricity. Grounding is a complex topic, but it is essential for electrical safety. By following the requirements of the NEC and by using good grounding practices, it is possible to create a safe and reliable electrical system. Here's more on grounding electrode systems. A grounding electrode system is a network of interconnected grounding electrodes designed to provide a low impedance connection to the earth. This connection is essential for the proper functioning of electrical systems, ensuring safety and mitigating the risk of electrical shock and equipment damage. The NEC specifies the requirements for grounding electrode systems, outlining acceptable types of electrodes and installation methods. Common types of grounding electrodes include metal underground water piped, concrete encased electrodes also known as UFA grounds, ground rings, rod and pipe electrodes, and plate electrodes. Metal underground water pipes, when in direct contact with the earth for at least 10 feet, can serve as effective grounding electrodes. However, supplemental electrodes are often required to enhance the system's performance. Concrete encased electrodes, typically constructed of at least 20 feet of bare copper conductor encased within concrete foundations or footings, offer excellent grounding capabilities due to the large contact area with the earth. Ground rings, consisting of a bare copper conductor encircling a building or structure and buried directly in the earth, provide a low impedance grounding path, especially in areas with poor soil conductivity. Rod and pipe electrodes, driven vertically into the earth, are a widely used and cost-effective grounding solution. The NEC specifies minimum dimensions and installation depths for these electrodes. Plate electrodes, buried horizontally in the earth, offer a large surface area for contact with the soil, making them suitable for areas with limited space for vertical electrode installation. The selection of appropriate grounding electrodes depends on various factors, including soil conditions, local regulations, and the specific requirements of the electrical system. Soil resistivity, a measure of the soil's resistance to electrical current flow, plays a crucial role in determining the effectiveness of grounding electrodes. Low soil resistivity facilitates the dissipation of fault current into the earth, enhancing the performance of the grounding system. Soil treatment techniques, such as the addition of ground enhancement materials, can improve soil conductivity and reduce soil resistivity, particularly in areas with poor soil conditions. The NEC mandates the interconnection of all available grounding electrodes to form a comprehensive grounding electrode system. This interconnection minimizes impedance and provides multiple paths for fault current to flow, enhancing the overall effectiveness of the grounding system. Grounding electrode conductors, sized according to the NEC, connect the grounding electrodes to the equipment grounding bus or the neutral bus within the electrical service equipment. These conductors must be adequately sized to safely carry a maximum fault current that could flow in the system. Regular inspection and testing of grounding electrode systems are essential to ensure their continued effectiveness. Ground resistance testing, using specialized equipment, verifies that the grounding system provides a low impedance connection to the earth. High ground resistance indicates a potential problem with the grounding system, requiring corrective actions to restore its functionality. Proper installation and maintenance of grounding electrode systems are crucial for electrical safety and the reliable operation of electrical equipment. Adhering to the NEC requirements and employing best practices ensures a safe and effective grounding system. Understanding the principles of grounding and the specific requirements for grounding electrode systems is essential for electrical engineers, electricians, and anyone involved in the design, installation, and maintenance of electrical systems. Now, let's elaborate more on equipment grounding. Equipment grounding is a critical safety measure in electrical systems, designed to protect individuals from electrical shock and minimize the risk of equipment damage. It involves connecting the non-current carrying metal parts of electrical equipment to the grounding system, providing a lower impedance path for fault current to flow back to the source. This connection allows overcurrent protection devices, such as circuit breakers and fuses, to quickly clear the fault, preventing dangerous voltage buildup on the equipment enclosure. The NEC outlines specific requirements for equipment grounding, specifying acceptable methods and conductor sizes. Equipment grounding conductors (EGs) are used to connect the metal enclosures of electrical equipment to the grounding system. These conductors can be either wires or metallic raceways, such as conduit or cable trays, provided they meet the NEC requirements for conductivity and mechanical strength. The size of the EGC is determined by the size of the overcurrent protection device protecting the circuit, as specified in the NEC Table 250.122. Larger circuits require larger EGC to safely carry the potential fault current. Grounding electrode conductors (GECs) connect the grounding electrode system to the equipment grounding bus or the neutral bus within the electrical service equipment. These conductors must be adequately sized to carry the maximum fault current that could flow in the system. Bonding is an essential aspect of equipment grounding, involving the interconnection of all non-current carrying metal parts of electrical equipment to create a low impedance path for fault current. Bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of electric shock. Bonding dumpers are used to connect metal enclosures, raceways, and other metal parts to the grounding system. These jumpers must be sized appropriately to carry the potential fault current. The NEC specifies requirements for bonding different types of metal enclosures and raceways. Listed and labeled grounding and bonding equipment must be used. This equipment has been tested and certified by a recognized testing laboratory to meet safety standards. The use of proper grounding and bonding techniques is crucial for electrical safety. Improper grounding or bonding can create a dangerous situation, increasing the risk of electric shock and equipment damage. Regular inspection and testing of equipment grounding systems are essential to ensure their continued effectiveness. Ground impedance testing verifies that the grounding system provides a low impedance path for fault current. High ground impedance indicates a potential problem with the grounding system, requiring corrective actions to restore its functionality. Understanding the principles of equipment grounding and the specific requirements of the NEC is essential for electrical engineers, electricians, and anyone involved in the design, installation, and maintenance of electrical systems. Adhering to these requirements ensures a safe and reliable electrical system. Neutral grounding is another concept. Neutral grounding refers to the practice of connecting the neutral point of an electrical system to ground. This connection provides a reference point for voltage and helps to stabilize the system voltage. Neutral grounding is essential for preventing overvoltages and protecting equipment from damage. The NEC specifies requirements for neutral grounding, outlining acceptable methods and conductor sizes. There are several different types of neutral grounding systems, including solidly grounded, impedance grounded, and ungrounded systems. In a solidly grounded system, the neutral point is directly connected to ground. This provides a low impedance path for ground fault current, allowing overcurrent protection devices to quickly clear the fault. Solidly grounded systems are commonly used in low voltage distribution systems. In an impedance grounded system, a resistor or reactor is inserted between the neutral point and ground. This limits the ground fault current, reducing the stress on equipment and minimizing voltage dips during ground faults. Impedance grounded systems are often used in medium voltage and high voltage systems. In an ungrounded system, the neutral point is not intentionally connected to ground. This type of system is more complex to protect and is typically used in applications where continuity of service is critical. The selection of the appropriate neutral grounding system depends on various factors, including the voltage level, the system configuration, and the desired level of protection. The NEC provides guidance on selecting the appropriate neutral grounding system for different applications. Ground fault protection is an important aspect of neutral grounding. Ground fault protection devices are designed to detect and interrupt ground faults, preventing damage to equipment and reducing the risk of electric shock. Ground fault circuit interrupters, GFCIs, are commonly used in residential and commercial applications to protect against ground faults. Ground fault relays are used in industrial and commercial applications to protect equipment from ground faults. The NEC specifies requirements for ground fault protection, including the types of devices required and the installation methods. Proper neutral grounding is essential for electrical safety and the reliable operation of electrical systems. Adhering to the NEC requirements and employing best practices ensures a safe and effective neutral grounding system. Another aspect is system grounding. System grounding refers to the intentional connection of a power system's neutral point or a designated phase conductor to the earth. This practice establishes a reference point for voltage, stabilizes the system, and provides a path for fault current to flow, enabling protective devices to quickly clear faults. The NEC outlines specific requirements for system grounding depending on the voltage level, system configuration, and application. The primary objectives of system grounding include limiting overvoltages, reducing the risk of electrical shock, and improving the coordination of overcurrent protection devices. Overvoltages can occur due to various factors, such as lightning strikes, switching surges, and insulation failures. System grounding helps to limit these overvoltages, protecting equipment from damage. By providing a low impedance path for fault current, system grounding facilitates the rapid clearing of ground faults, minimizing the duration of fault currents and reducing the risk of electrical shock. System grounding also improves the coordination of overcurrent protection devices, ensuring that the device closest to the fault opens first, minimizing the extent of the outage. There are several types of system grounding configurations, each with its own characteristics and applications. These include solidly grounded systems, impedance grounded systems, and ungrounded systems. In solidly grounded systems, the neutral point of the transformer or generator is directly connected to earth. This configuration provides a low impedance path for ground fault current, allowing for fast fault clearing. Solidly grounded systems are commonly used in low voltage distribution systems. In impedance grounded systems, a resistor or reactor is inserted between the neutral point and earth. This impedance limits the ground fault current, reducing the stress on equipment and minimizing voltage dips during ground faults. Impedance grounded systems are often used in medium voltage and high voltage systems. In ungrounded systems, there is no intentional connection between the system conductors and earth. While offering some advantages in terms of service continuity, ungrounded systems are more complex to protect and can experience transient overvoltages during ground faults. The selection of the appropriate system grounding configuration depends on various factors, including the voltage level, the size and type of load, and the desired level of protection and reliability. The NEC provides guidance on selecting the appropriate system grounding configuration for different applications. Grounding impedance, which can be either resistive or reactive, plays a crucial role in determining the magnitude of ground fault current and the resulting voltage rise during a fault. The selection of the appropriate grounding impedance value requires careful consideration of system parameters and protection objectives. Ground fault protection devices, such as ground fault relays and ground fault circuit interrupters, are essential components of system grounding systems. These devices detect ground faults and initiate the tripping of circuit breakers, isolating the faulted section of the system and preventing further damage. The NEC specifies requirements for ground fault protection, including the types of devices required and the installation methods. Proper system grounding is crucial for electrical safety and the reliable operation of electrical systems. Adhering to the NEC requirements and employing best practices ensures a safe and effective system grounding system. Here's more on bonding. Bonding is the process of connecting together all non-current carrying metal parts of an electrical system to create an electrically conductive path. This path ensures that all metal parts are at the same electrical potential, minimizing the risk of electric shock and providing a low impedance path for fault current to flow back to the source. The NEC provides detailed requirements for bonding, specifying acceptable methods and conductor sizes. The primary objectives of bonding include minimizing the risk of electric shock, providing a low impedance path for fault current, and reducing electromagnetic interference. By connecting all metal parts together, bonding eliminates potential differences that could cause electric shock. The low impedance path provided by bonding facilitates the rapid clearing of ground faults, minimizing the duration of fault currents and reducing the risk of equipment damage. Bonding also helps to reduce electromagnetic interference, ME, by providing a path for unwanted currents to flow back to the source. There are several different types of bonding, including equipment bonding, service bonding, and structural steel bonding. Equipment bonding involves connecting the metal enclosures of electrical equipment, such as motors, transformers, and distribution panels, to the grounding system. Service bonding involves connecting the neutral conductor of the electrical service to the grounding electrode system. Structural steel bonding involves connecting the metal frame of a building or structure to the grounding system. Bonding jumpers are used to connect metal parts together. Bonding jumpers must be sized according to the NEC, based on the size of the circuit conductors. Bonding conductors can be made of copper, aluminum, or other conductive materials. The NEC specifies requirements for the type of material and the installation methods for bonding conductors. Bonding lockouts and bonding bushings are used to connect metal conduit to electrical enclosures. These fittings provide a secure and conductive connection, ensuring that the conduit is properly bonded to the enclosure. Bonding straps are used to connect metal parts that are not directly connected to each other. Bonding straps must be sized appropriately to carry the potential fault current. Proper bonding is essential for electrical safety and the reliable operation of electrical systems. Improper bonding can create a dangerous situation, increasing the risk of electric shock and equipment damage. Regular inspection and testing of bonding connections are essential to ensure their continued effectiveness. Understanding the principles of bonding and the specific requirements of the NEC is essential for electrical engineers, electricians, and anyone involved in the design, installation, and maintenance of electrical systems. Adhering to these requirements ensures a safe and reliable electrical system. Let's also talk about surge protection. Surge protection is the practice of protecting electrical and electronic equipment from voltage surges, also known as transient overvoltages. These surges can be caused by lightning strikes, switching operations, and other disturbances on the power grid. Voltage surges can damage or destroy sensitive electronic components, leading to equipment failure and costly downtime. Surge protection devices, SPDs, are used to mitigate the effects of voltage surges. SPD work by diverting the surge current away from the protected equipment, limiting the voltage that reaches the equipment. The NEC provides requirements for surge protection, specifying the types of SPD required and the installation methods. SPD are typically installed at the service entrance of a building, as well as at the point of use for sensitive electronic equipment. SPD are rated by their surge current capacity, which is the maximum amount of current that the SPD can safely divert. The surge current capacity of the SPD should be selected based on the expected surge current levels at the installation location. SPD are also rated by their voltage protection level, which is the maximum voltage that the SPD will allow to pass through to the protected equipment. The voltage protection level should be selected based on the voltage withstand capability of the protected equipment. There are several different types of SPD, including metal oxide varistors, MOVs, silicon avalanche diodes, and gas discharge tubes. MOV are the most common type of SPD. They are relatively inexpensive and provide good surge protection. Silicon avalanche diodes are faster than MOV and provide better surge protection for sensitive electronic equipment. Gas discharge tubes are used for high-energy surge protection applications such as lightning protection. SPD should be installed in accordance with the manufacturer's instructions and the NEC requirements. Proper installation is essential for the SPD to function effectively. SPD should be inspected and tested regularly to ensure that they are functioning properly. SPD can degrade over time due to repeated exposure to voltage surges. Surge protection is an important aspect of electrical safety and the reliable operation of electronic equipment. By installing SPD, it is possible to protect equipment from damage caused by voltage surges. Now let's examine lightning protection. Lightning protection is a system designed to protect structures and people from the harmful effects of lightning strikes. Lightning strikes can cause fires, explosions, and electrical shocks, leading to significant property damage and personal injury. A lightning protection system typically consists of air terminals, also known as lightning rods, conductors, and grounding electrodes. Air terminals are installed on the highest points of a structure to intercept lightning strikes. Conductors are used to carry the lightning current from the air terminals to the grounding electrodes. Grounding electrodes are used to dissipate the lightning current into the earth. The NEC and other standards, such as NFPA 780, provide requirements for lightning protection systems. These standards specify the types of materials and installation methods that must be used. Air terminals should be made of copper, aluminum, or other conductive materials. The size and spacing of air terminals depend on the size and shape of the structure. Conductors should be made of copper or aluminum. The size of the conductors depends on the expected lightning current levels. Grounding electrodes should be made of copper or steel. The number and spacing of grounding electrodes depend on the soil resistivity. Lightning protection systems should be installed by qualified professionals. Proper installation is essential for the system to function effectively. Lightning protection systems should be inspected and tested regularly to ensure that they are functioning properly. Lightning protection is an important safety measure for structures in areas with high lightning activity. By installing a lightning protection system, it is possible to significantly reduce the risk of damage and injury from lightning strikes. The grounding conductor should be connected to a grounding electrode that is buried in the earth. The grounding electrode should be located as close as possible to the electrical service entrance. The grounding conductor should be sized according to the NEC. The grounding conductor should be protected from physical damage. Grounding is an essential safety measure in electrical systems. By properly grounding electrical equipment, it is possible to reduce the risk of electric shock and equipment damage. It's important to understand the NEC requirements for grounding and to follow good grounding practices. Here's more on electromagnetic interference, EMI. Electromagnetic interference, EMI, is a disturbance caused by electromagnetic radiation that can disrupt the performance of electronic devices. EMI can be generated by a variety of sources, including radio transmitters, microwave ovens, electric motors, and even other electronic devices. EMI can cause a variety of problems, including data corruption, system malfunctions, and reduced performance. There are two main types of EMI: conducted EMI and radiated EMI. Conducted EMI is transmitted through electrical conductors such as power cords and signal cables. Radiated EMI is transmitted through the air in the form of electromagnetic waves. There are several techniques that can be used to mitigate EMI, including grounding, shielding, filtering, and cable management. Grounding provides a low impedance path for unwanted currents to flow back to the source, reducing the amount of EMI that is radiated or conducted. Shielding involves enclosing electronic devices in a conductive enclosure to block electromagnetic radiation. Filtering involves using filters to block unwanted frequencies from entering or leaving electronic devices. Cable management involves routing cables in a way that minimizes the amount of EMI that is radiated or conducted. Proper grounding is essential for mitigating EMI. All metal parts of electronic devices should be properly grounded to provide a low impedance path for unwanted currents. Shielding can be used to reduce both conducted and radiated EMI. The effectiveness of shielding depends on the material used, the thickness of the shield, and the frequency of the EMI. Filters can be used to block unwanted frequencies from entering or leaving electronic devices. Filters are typically used on power cords and signal cables. Cable management can help to reduce EMI by minimizing the length of cables and by keeping cables away from sources of EMI. EMI is a complex problem, but it can be mitigated by using a combination of techniques. By properly grounding, shielding, filtering, and managing cables, it is possible to reduce the amount of EMI that is generated and to protect electronic devices from its harmful effects. Remember that the source book on grounding, while comprehensive, might need to be supplemented with more recent information or specialized text depending on specific needs.